Well, good afternoon. This is 12:22. We're 7 minutes late getting started for Calculus 3, and right now I'm still the only one in the room, so hopefully some more will be coming in soon. Let me go and get from the current slide. I think I'll wait until somebody comes in the room before I make the other announcement, but I do have a couple things that we need to talk about. Let me do say this, though, now. This class, we're, I guess, down to 1, 2, 3, 4, 5 students, and I've received 3 papers from the 5 students. So, need to get those other 2 in soon, folks. And let's see, one person still hasn't turned in test 1. And only one person has turned in test 2. And I'm ready to give you test 3, but that's the subject of the other announcement, but I'll wait until someone else comes in the room before we go into that. So listen up on the video until you hear me talk about that. Anyway, where we left off last time, we just got started in chapter 14, and we're in 14.1 on page 971. We had just done example 2, so a little bit of a review of that. There was example 2, okay? And believe we had accomplished that, and now they were making comments about it, okay? That was example 2. It said the integral in example 2 is an iterated integral. The brackets used in example 2 are usually not written. Instead, they're usually written just with the double integrals like this. So the integral, and here's the characteristics of it, by the way. All right. Your function is a function of x and y, okay? Or any other 2 variables, 2 variable function. That's why you need the double integral. Okay. Now, there's a function of x and y, say, or any 2 variables. All right. Now, if you know the limits, if you integrate this with respect to y, y, remember, can be some function of x, okay, like these g's here. But so you can integrate this function with respect to y only, leaving your x alone, treating that like a constant, leaving it alone, and integrate with respect to y, but then plugging in the values of x, the g of x that's going between, could be 1 or only 1, either top or bottom, or both, or neither. They could just be numbers here. That would be fine too. But anyway, you lose your y's because you integrate those out, and then you're left with functions of x, either from the f of x, y, which you've already integrated the y's out, or the g's that you plugged in, but they're all functions of x. So then you do your last integral with respect to x. Now these limits here must be numbers, okay? They cannot be a function of x or y. They have to be letters or numbers or something, but they can't be functions of either x or y. Now, if that wouldn't work that way because you didn't have y's as functions of x, but you had x's as function of y, or expressed as functions of y, then do the integration with respect to x first, and have your function with respect to y being the limits here. You integrate f of x, y, not doing the y's, keeping those, just treating those like a constant, but only integrating with respect to x, and then plugging in, if those are functions of y, plug those in for the x's, or if one or other is not, that's fine. And then when you finally do the last integration, everything will be in terms of y. You got rid of your x's when you integrated them out here. Now you have the y's left from the f of y and the h's of y. But then when you integrate that, you better have numerical or, plain limits there, no functions. The inside limits of integration can be variable with respect to the outer variable of integration. That's what I was saying. However, the outer limits of integration must be constant with respect to both variables of integration. And that's what I was saying too. They phrase it differently though. Okay, after performing the inside integration, you obtain a standard definite integral, and the second integration produces a real number. The limits of integration for an iterated integral identify two sets of boundary values for the variables. Okay, now that's not totally clear what they're talking about there, but I have a feeling they're going to explain it later. Okay, for instance, in example 2, the one we just did last time, the outside limits indicate that x lies in the interval from 1 to 2. Okay, the inside limits indicate that y lies in an interval of 1 to x. Okay, so you see there's a variable x, so that has to be integrated first, the innermost integral. Okay, together those two intervals determine the region of integration of r, which is of the iterated integral, and that's shown kind of here. Okay, yeah. The function y is equal to 1 basically is this, and the function y is equal to x is this. So you're integrating whatever was in here, and you're integrating on this, and you're only going from 1 to 2, so you're only integrating over that region right there. Okay? But where you have the variable here, that means you have to do the integral with respect to y first, as it goes from 1 to x. And when you integrate that, you lose the y's altogether, and then you integrate again with respect to x and go, which we already did. All right. That was example 1 and 2, the verbiage about it, and now we're moving to the area of a plane region. All right. So let's consider a plane region R, and this plane is going to be on the XY plane. Might as well put it there. That's where we usually are. And it's bounded by, X is bounded A on one side, B on the other. So that, you know, is going to be your last integration, the outer integration, because those are pure numbers. But the Y is, the Y is bounded by a G of 2 on top and a G of sub 1 on the bottom. Okay, so G sub 1 of X is always less than or equal to Y, and that's less than or equal to G2 of X. Okay, now, sort of shown there, so it's a plane region bounded by functions of X. Y is a function of X, or actually here, G's are functions of X, but the X is bounded by A to B. So the area of R would then be, just like we did before, the length of this little rectangle, that's G2 minus G1, times the thickness of that little rectangle, that's your dx or your delta x, and you integrate from A to B to get there. Okay? So using the fundamental theorem of calculus, you can write the integram G2 of x minus G1 of x as a definite integral. Okay? All right. Specifically consider the x to be fixed and let y vary from G1 of x to G2 of x. You can write the integral see what they're saying here. All right. What they're saying is the thing that's in here, right here, you can refer to that as an integral of y going from G1 to G2, which is exactly what they did here. An integral of dy, antiderivative of dy is just y, evaluated here, G2 minus G1, okay? combining those two, then this is the one up here that produces the difference there, and then the last one is the ones with limits, and that's on the x, going from A to B. Okay, so you come back to the same thing we just had. All right, now placing a representative rectangle in the region R helps determine both the order and the limits of integration. A vertical rectangle implies the order dy then dx, okay, with the inside limits of integration corresponding to the upper and lower bounds of the rectangle, is shown in this figure here. Okay, same thing we've done. Not too sure what the difference in that in the last slide was. It's very, very similar. Okay, now this type of region is called vertically simple. You don't have any, okay, because the outside limits of integration represents the lines x equal A and x equal B. Okay. Trying now to remember if there's any easy way to remember that's vertically simple. Seems like to me with simple limits that the horizontally simple, but no. Okay, here's what they mean by vertical. Okay, it's vertically simple because you're going from one function to another. If you're trying to do this horizontally, you would have some areas here where you're going from this to that, for instance. Others you're going from this one to that one. You know, I'm sorry, this to that. You're going from different parts of the same. That's not at all simple, okay, to integrate it horizontally. Not simple, because you have different region you're going from. Vertically, same region on top, same region on bottom, vertically simple. Similarly, horizontal rectangle implies the order dx dy with the inside limits of integration determined by the left and right bounds of the rectangle. That is horizontally simple because the outside limits of the integration represent the horizontal lines, and from y equals c to y equal d. Okay. All right, the block at the bottom of page 972, area of region of a plane. If R is defined on some region, A to B on X, G of X, G1 of X to G2 of X on Y, G1 and G2 are continuous on AB, then the area of R, that region that we're talking about, is the integral. The outside integral would be the one with the numerical limits A to B, and that's a dx, so that's the outside d on it, because that's what x is going to. And then the inside integral would just be from g1 of x to g2 of x dy. This is just to get its area, okay? You're not interested in any other features of a function, just the area. If R is defined, y is defined between two limits, and x is between two functions of y, h1 of y and h2 of y, where they're continuous everywhere on C to D, then the area of R, you just reverse the order of integration to get the variable limits on the inside and the constant limits on the outside, variable limits here being the x variables. X is a function of y, x going between h1 of y and h2 of y. So you do that first and then do the integral on the outside, which is with respect to y going from C to D. If you notice a little problem with my speech, this room is cold. I'm having trouble keeping my hands warm, keeping my head unclogged. It's just this. They did this Monday and got it fixed, and then today I thought they would probably be monitoring it. They're not. But then I'm cutting them a little slack today because evidently there was an explosion on the Birmingham West campus last night sometime, and so probably all maintenance is over there trying to sort through that. I don't know that for a fact, but I sure haven't seen anyone around here today, so I'm going to just give them the benefit of the doubt that they're doing that. And by the way, when you do the area and the whichever is the innermost integral, if it's y, then it's vertically simple. If it's x, it's the horizontally simple. All right, finally we get to example 3. Use an iterated integral to represent the area of the rectangle shown in figure 14.4. Okay? Boy, so much easier just to do it, but let's do what they say. Here, since you have numerical limits both ways, it doesn't matter which one you do first. You can do the integral from C to D for a second, outer, and then do the integral from A to B. Well, glad you could make it today. Yeah. Glad you're here because it's kind of boring talking to myself. You say it's boring for me to talk to you. Is that what you said? Oh, I heard that. Okay. All right. Let me first turn on the projector. Please get a light on for you. There's so much light coming in. Right now, I'll take any light I can to warm this room. It is cold. It is today. What's that? Today. Mm-hmm. And the only reason I haven't called to bug them, did you hear there was an explosion on the Birmingham campus? Yeah. Yeah. What happened? I have no idea. Someone said it was the C building, which is where math classrooms are, and then the biology labs. There's a couple of biology things upstairs, and I heard it was a pretty major fire there. Now, evidently, from just one person talking, it sounded like it didn't go to either the library building or the B building, but they said it was a pretty major fire in the C building, which is sort of surprising because the C building is really small. There's really nothing on the ground floor that I can imagine could explode. There's biology labs upstairs which might have something that could explode, but they said it seemed to start on the ground level. So I don't have any idea, but they said the classes that normally meet in the C building were meeting in the gym. Yeah, the gym and the ACAT building. Okay, now ACAT building makes sense. Yeah, the gym. Why meet there? You know, because there's, in my mind, should be plenty of rooms in the ACAT building. I mean, that's a pretty good sized building. Not that many people use it. No, so. Right. There's plenty of rooms in the ACAT building. I've been there before, so I don't know why they chose. But it may be when they're saying the gym, they mean the art classrooms and there's a few like that, but it doesn't look like there could be that many. But maybe there are. I've never been over in that classroom wings. I don't know. So anyway, I decided not to bug them because I figured they're probably pretty busy. They may not be, but it just seemed like it might be. All right, we're on page 973. Chapter 14, multiple integration, 14.1, iterated integrals and area in the plane. And we're doing the area in the plane now. And here is the problem. Use an iterated integral to represent the area of the rectangle shown in this figure here. So I just arbitrarily said, and since it's a rectangle and no side depends on the other variable, it doesn't matter which order you do. So I just arbitrarily put C to D on the outside and A to B on the inside. And since you're doing an area, you don't really have an argument here. No function inside here, just one. And then what would you do next? What's the next thing to write down? Believe me, it's really simple.
We start with A.
What's that?
Start with the 8. Will I start with the
No, I don't have a full integral written down there. I only have the first two elements of the integral. What's missing? Whenever you have an integral sign here, you better have something over here. What is it? No, it's 2. Well, always accompanies an integral sign at the end. Yeah, exactly. So what do I put? I will have a dy in there. Tell me where to put it. First or second?
Would it be the first? No, the second.
The second, the outer one, because C to D is going on Y. So that's your dy. So that would mean that A to B is going over dx. And that's a pretty ugly x. And that's it. That is your iterated integral to represent that. Okay? Okay? Well, let's integrate it. What is the integral of, you always do the integral one first. What is the, so just write down, oh, here we have Muhammad. Okay. All right, so the outer one we're not going to mess with yet. That's going to be C to D. And we'll leave the dy out there by itself. So how do we integrate dx? What's the antiderivative of dx? X. Okay? And the x is evaluated from A to B. Okay? So this will be the integral from C to D. And what is x evaluated from A to B? No, okay, no, you're evaluating it. This is x equal b, this is x equal a. So that would be fundamental theorem of calculus. Tells you that's b, the upper one, minus a. And then this is times dy. Okay, now since there's no y variation in either one of these, that's just a number. That's just a constant, right? Those are constants. A and B are constants, so the difference of A and B is constant. So you can pull that on the outside. Okay, you don't have to, but you could. B minus A, that's just some number, times the integral from C to D of dy. And what's that? B minus A d minus c, exactly. The antiderivative of dy is y, and then you evaluate that between c and d, so it'd be d minus c. Okay? And of course, b minus a is the length on the along the x-axis, and d minus c is the length along the y-axis. Length times width is the area of a rectangle. Of course it is, right? So like I said, you could have done this without calculus so much easier. Instead, that's length, b minus c times width, b minus a. That's the area of the rectangle. But you got it through calculus too. Right? All right. They say, notice that this answer is consistent with what you know from geometry. Yeah? Okay. Well, let's see how they did it in case they did anything a little differently that might be of interest to you. The region shown is both vertically simple and horizontally simple, so you can use either order of integration, and they actually did the reverse of what we did. Okay? Goodness gracious, my hands are so cold. Sorry, got to warm up some. All right, so they did this one first. And if you, Oliver, you go back to work?
No, it's not working. I have someone has seen this.
Okay, so do the inner one first, Antiderivative of dy is just y, so that's all that is. Evaluate it from c to d, and in doing that, that would be integral from a to b of e plus y equals d minus y equals c. So d minus c dx. So that's going to be the next step. The integral from b to a of d minus c times dx. D is a constant, c is a constant, d minus c is a constant. Pull it on the outside. They didn't, but you could have. And then you integrate dx, or you just count that as a number. Integrate a constant dx, it would be the constant times x. Evaluated from a to b. So plug in for this, d minus c times b minus d minus c times a, which is d minus c times b minus a, which is just the length times the width, which is a rectangle. That's the area of a rectangle. Notice this answer is consistent with what you know from geometry. Oh, that's the last slide. Oh, there is an example 4 here, which I guarantee you is a little more complicated than the last one, and they leave it off, of course. Use an iterated integral to find the area of the region bounded by the graphs of f of x is equal to sine x, okay, and g of x is equal to cosine x, okay, between pi force and 5 pi force. Okay, in that integral, I'll put them in bracket. Okay. Ooh. All right. So it may be helpful, I think it probably would be, to sort of draw a graph. Okay? Now, okay. Sine starts at 0, and at pi halves goes up to 1. At pi goes down to 0. At 3 halves pi goes down to minus 1. At 2 pi, it goes up to 0 again. Okay? That's going to be more than enough for this interval. Okay? The cosine, what color you want cosine to be? Blue. Okay? All right. Cosine starts at 1, goes down to 0, down to minus 1, up to 0, and up to 1 again. Okay? So cosine does something like this, and sine does something like that. Okay? So we want the region between pi fourths, which is right here, and 5 pi fourths, which is right there. It's in between pi, which is 4 fourths pi, and 3 halves pi, which is 6 fourths pi. It's right there in between. So, we're talking about little rectangles that are formed like this. Now, because that's what we call vertically simple, you can draw vertical lines between the two curves everywhere without having to back up. Not horizontally simple, because if you did it horizontal, this rectangle between sine and sine, these would be between sine and cosine, these down here would be between cosine and cosine. Not simple at all. But these, between sine and cosine, sine and cosine, sine and cosine, yeah, all of those are between the same two functions. Okay? So, we want the area, I think it was, find the iterated, use an iterated integral to find the area of the region bounded by the graphs of those two functions between those 2 points. Okay? So, since we know the actual values of the limits of x, that needs to be our outside interval, right? Because we know x is going from 5/4 to 5/4. That's what we told us. Okay? So our external integral is going to be this. And it's going from 5/4 to 5/4. And it's going to be a dx on the outside. Okay. Now, the y's, hands are cold, just freezing. And I'm usually hot, I mean, so I know the room has to be cold. Okay. The y's are going from sine to cosine. So we're integrating that from cosine x to sine x. That's going to be the y's. Okay? So the y will be going from, the lower one is cosine x, the upper one is sine x. And so that's going to be your dy's there. There's no integrand in the middle because we're just integrating the area. Nothing else. We're not evaluating something that has a surface in there, just the area. Okay? Now, what do you do first, the inner or the outer? No, always inner first. That's always together. Always start there. So the outer you leave alone. That's going from 5/4 to 5/4. And the dx is out there. But we're going to integrate that. Now, what is the antiderivative of dy? Y. Let's see, y, and it's evaluated from cosine x to sine x. Okay? I'm going to need more room, possibly. This will be the integral from 5/4 to 5/4. Okay? Now, we're doing that in the middle. And this is going from y is equal to cosine of x to y is equal to sine x. Y is equal to sine x minus y is equal to cosine x, right? That's how you evaluate that. Upper minus lower. So that would be sine x minus cosine x. Okay? dx. All right. Brr. All right. I'm going to go up top to finish this, I think. The integral. No, let's not do the integral anymore. Okay. Let's actually do the integration. Okay. What's the antiderivative of sine x? Say again? Of sine x. I believe it's minus cosine x. Because when you take the derivative of cosine, it's minus sine. In order to get a positive sign, you have to do the derivative of minus cosine. Okay? And antiderivative of minus cosine x would be minus sine x. Okay, now we do the subtracting. No, that's the antiderivative. And now we plug in, and by the way, we should have drawn. No, I'm sorry, keep forgetting. We've already done that. Okay, we've already integrated it. We just did. Okay, and this is going from 5/4 to 5/4. Okay. Oh, man. Okay. Now, I swore that I was going to stop skipping steps because I was afraid I might be losing people. But man, when I have so little room, I want to skip some steps. But let's just plug it in and see what we get. Okay? We have a minus cosine plugging in the top value, 5 pi over 4 minus sine of 5 pi over 4, okay, minus plugging in the bottom one, a negative cosine pi fourths minus a sine of pi fourths. Okay. Goodness gracious, I'm so stiff. Okay. Now we got to do some head scratching here. What is the cosine of 5 pi fourths? Well, it just happens we have it on our thing. Oops, right there. That's what? What value?
2.
Nope. Negative 1 down here. So what value is that?
Oh,
Okay, what is the value of every quarter pi? Absolute value. Sine or cosine? At the quarter pies. All the quarter pies have the same value basically. Just the plus or minus. Remember what it is? Sine of pi fourths, say? Right here? What is sine of pi fourths?
square root of 2.
Square root of 2 over 2.
Yeah.
Okay, square root of 2 over 2. So down here it's minus square root of 2 over 2, right? Okay. So at the first value, it's a minus root 2 over 2, but there's a minus in front, so that's a root 2 over 2. Okay? Minus, and what is the sine of 5 fourths pi? Well, that happens to be negative root 2 over 2 also. So that's minus, which is again a plus root 2 over 2. Okay? Now, let's go to the other side. And we have a minus and minus here, so that makes a plus, right? Plus cosine of pi fourths. And what's cosine of pi fourths? Square root 2 over 2. Okay? That's what they always are at the quarter pies. So it's plus another square root of 2 over 2. And then you got a minus, which is a plus. What's the sine of pi fourths? Root 2 over 2. Okay? Now you add those together, you get 4 root 2's over 2, which would be 2 root 2. And you can plug that in the calculator and see what you get. Something around 5.8 or something like that. I don't know. I'm just making up a number. They don't do 1. They just say 2 root 2. Okay? See how it works? Okay. Now, again, this is vertically simple because all your rectangles here go from one curve to the other curve. Okay? You don't have any places where they're doing different portions of different curves. So you're perfectly fine. That's vertically simple. Not that they're fixed values, but they are fixed rectangles. Okay. Now, Okay, I was right. I was trying to think. Was there another slide? No, there isn't. But there's at least 2 more examples. So it looks like we got some more to do. I apologize for my voice. I'm hoarse. I've got conjunctivitis in my right eye. Everything's hurting. My knee is hurting. And that has nothing to do with any of the others. So here's example 5. Comparing different orders of integration. And you can see larsoncalculus.com for an interactive version of this type of example. Okay? Now, sketch the region whose area is represented by this integral. You're going from 0 to 2, and you're going from y squared to 4. And as soon as you see the y squared there, you know this has to be the dx first and the dy later. Okay? Why? Because when you integrate with respect to x, you count the y's as constants. So it's okay to have that there. You couldn't be integrating y's because when you evaluate, you wind up with y's where y's should have been. So no, that doesn't work. So you know it's a dx first, dy later. So now, as soon as you see this, what the problem says is not necessarily find the answer. It says sketch the region whose area is represented by that. Notice there's no integrand there, so this represents an area. Okay? Now, let's draw some axes here. Everything's positive. Okay, the y is going from 0 to 2. And the x's are going from something to 4. Okay? All right. Now, the something there was y squared. Okay? Now, since we drew the x-axis horizontally, like we usually do, and the y-axis vertically, like we usually do, you don't have to, but we did. Okay. I know right now this end bound is 4. That's what it's going to, 4. It has to be an end there, always 4. Okay, now what does the function x equal y squared look like? Well, basically what to say, this is from x equal 4, ultimately from x equal y squared to x equal 4. So x equal y squared, what would that look like? If you're plotting that function, x is equal to y squared. Because then x sort of is acting like the dependent variable, and y is your independent variable. I'd say, give me a y. So give me a y. Y. And if x is y squared, then I don't have mine set up to. Let me see if I can clean that up just a little bit. Let me order these things a little bit better. I may not have room to, but let me try anyway. Okay. That's a little better. Okay, here's your 4 out there. And this is what x equal 4 is going to somewhere out there. So x equals y squared. So when you say y was 1, x is 1. So there it is right there, 1, 1. Give me another y. 2. Okay. When y is equal to 2, what's x equal to? Remember, we're doing x is equal to y squared. That's the lower limit here, x equal y squared. The upper limit is x equal 4. There's x equal 4 right there. So when y is equal to 2, what is x equal to? X equal y squared, that would be 4. So there that point is. That's on the end. So don't give me any y's any greater. Give me something in between maybe. Well, less than.
less than 1? 0. When y is equal to 0, what's x? 0. This is what this is looking like. Okay? It's half a parabola, right? So this would be that part. So y is going from 0 to 2. X is going from y squared. Here's your function y squared to 4. Okay? And since things are in terms of y, this is going to be my dy here. Okay? So that's what was it? Ooh, goodness. Oh, no, okay. This is the area that you're calculating when you do this function. Okay? Has to be x going from y squared, which is this curve here, to 4. And y is going from 0 to 2. Okay? That would be the area. Now, my parabola isn't too pretty. It's kind of ugly, in fact. But don't laugh. Okay. All right. Oh, that's late, but okay. All right. Now, if on the other hand, you had wanted to, for some reason, to do a dy and then a dx, okay? Now, the outer band here is your x, and the inner integral is your y, okay? Well, if you're doing a dx last, okay, then that means this is going to be our rectangle, okay? Now, the question is, if this is a dx, you want this function in terms of x. What is that function in terms of x? What is this a model for? I probably didn't get it quite good. Still not great, but something like that. What is that? It's too flat at the top. Get both of those off of there. Okay. That's a little bit better. What's that a function? What function does that describe? Any idea? What's that graph of in terms of x? Guess what? It's related to y is equal to x is equal to y squared. Solve that for y. What do you get? No, it isn't. How did you get that? How did you go from y squared to y? What function will take you there? It's sure not the squaring function. If you were squaring, that would be y squared to y fourth. That's not what we got. We got y squared to x. Y squared is equal to x. What would y equal to? How do you undo a square? No, that's division. You undo division by multiplying. How do you undo a square? Second?
You said I undo the square?
Yeah.
Take the square root?
Yes, of course. So this would be y is equal to the square root of x. And isn't that what the square root of x looks like? Give me an x, 0, square root of 0 is 0. Give me an x, 1, square root of 1 is 1. Give me an x, 4, square root of 4 is 2. Yes, this is the square root function in x. There's a squaring function in y, square root function in x. And here we only use the positive part because we're going from 0 to 2 and 0 to 4. Okay? So therefore, in this rendition, you would be going from the y's first. Y is equal to 0 to this function here. That would be 0 to the square root of x. Because that is that function here, y is equal to the square root of x. And then your x's are going from 0 to 4. the last one always has to be numeric. Okay? So, Justin's here. Now, I didn't quite understand. Where was Muhammad going? Oh, he's on the phone. Oh, he said home, I guess is what he said.
Yeah, I think he said something on the seat.
Yeah, I think that's what he said. Okay. So this is how you would set up that. Again, no integrand, because there's nothing to integrate. You're just finding an area. And that would then be from the y going from 0 to the square root of x, and the x then going from 0 to 4. The outer one always has to be between two numbers. The inner one can be to or from either or a function, or both. So you see how you go back and forth there? Solve that one for the other, solve one for the other. Now, if that was some real big, hairy, miserable-looking function that you can't solve in terms, then you can't do this. The functions that you can solve in terms of one another, yeah, you can do that. Okay? Any questions on that? That was example 5. Oh, are we supposed to actually, why don't we evaluate it? Okay. I didn't know they wanted us to do that. Oh, okay. Sketch the region, blah, 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 then find another iterated integral using the order dy dx, which we just did, to represent the same area, and show that both integrals yield the same value. We haven't done that yet. So, let's do this integral first. What would that integrate as? I'm going to, I don't remember what that line was there for, but I'm going to erase it. And I'll erase that one too. I don't know what that's there for. It must have had a reason at some point, but it doesn't anymore. Let's evaluate that integral right there. Which one do we do first? Inner or outer? Huh? Inner, very good. So let's do this one first. Okay. So we're going to leave the 0 to 2 alone for now and the dy alone for now. Okay. Now what's the antiderivative of the dx? X. And you're going from x equals 4 minus x equal y squared. So there's your first integral, right? Duh. Okay. Duh. Okay. Now let's integrate that. What would that integrate as? Antiderivative of 4 is 4y, exactly. Minus, what's the antiderivative of y squared? Say again?
You say y squared, right?
Yeah, y squared. Antiderivative. Y cubed over 3. We'll evaluate that from 0 to 2. Okay? I'll do the 0 part, you do the 2 part. When you plug in a 2, what do you get? 4 times 2 is 8, minus, plug in a 2, second, 2 cubed is 8 over 3. Okay? Goodness, my eyes hurt. Well, 8 is 24/3, right? At least common denominator would be 24/3 minus 8/3 is what? 16/3. What do you get? Another day? Oh, no, that's a different thing. Okay. Now let's integrate the other one there. I'll try to do this above it. In fact, what I think I'm going to do is reduce that a little bit because that's a lot of wasted space. Okay. And ooh, that's not an eraser. Okay. There we go. 0 to 4, 0 to the square root of x, dy dx. Okay. So you're doing the integral from 0 to 4, 0 to square root of x, dy dx. Okay? And what do you do first? Inner. Okay, we do the inner one first. So we'll leave this alone, 0 to 4. It's going to stay that. The dx will stay that. Okay? And what's the antiderivative of dy? Y. Why not? Okay? So it'll be y evaluated from 0 to square root of x. Okay? And that would be the integral from 0 to 4 of, when you plug in y is equal to square root of x, you get square root of x minus 0 dx. Okay, now I don't like integrating square roots, so I'm going to rewrite that as what in second, x to the 1/2. Exponential notation is what I was trying to say. So that would be x to the 1/2 dx. And what's the antiderivative of x to the 1/2? X to the 3/2. Okay, that's a good start. Okay, I'm going to do it up here. X to the 3/2. But you have to have some coefficient there. What would that be? It's either divided by 3/2 or... No, okay, you're going the wrong way. You always put it over the exponent. So it's divided by 3/2, but what's it the same as? Dividing by 3/2 is the same as? Doing what with 2/3? Multiplying by 2/3. So let's make that 2/3 times that. Now this we're evaluating from 0 to 4. Okay? That's an ugly 2. I was trying to figure out what in the world that was. All right. Now, when you plug in the 4, since that is a perfect square, I like to do the square root first. The square root of 4 is 2. 2 cubed is 8. And 2 times 8 is 16 of the 3. All right? That was exciting, wasn't it? 16/3. And then when you plug a 0 in, you get 0. Right? Everybody follow that? What's that? Okay. You'll understand that. Plug a 0 in for the x. Okay. All right. All right. Good. Oh, that's going to be hard to eat.
It's not that bad. I can get that.
Okay. But you see, we did it the first way, and what did we get? 16/3. We did it the second way. We got 16/3. Makes you feel warm and fuzzy inside, right? Because you better get the same answer if you do the right stuff both ways. Right? Okay. So that was example 5. Well, we still don't have any more room, so we're going to use the same space. Can I erase it, or do you need it up there a little longer? Erase? Okay. Now let's do example 6. Find the area of the region R that lies below the parabola y is equal to 4x minus x squared. Okay. And above the x-axis, okay, so it's below this, above the x-axis. Now, can you write the x-axis for me in terms of an equation, since that is a form of equation, what is the x-axis as an equation? Preferably y is equal to something. The x-axis, y is equal to what? Everywhere on the x-axis, y is equal to, second, let's draw a little thing here, okay? Gonna have to anyway, sometime anyway. Here's the x-axis. What is y equal to every place on the x-axis? 0. So y is equal to 0. When it says above the x-axis is where y is equal to 0. Okay? And above the line, y is equal to negative 3x plus 6. Okay. So those are our conditions. Below the parabola, above the x-axis, and above this line. Okay? So we need to draw in the parabola. Okay? So let's start with it. Give me an x. 1. Okay? Okay. At x equal 1, what is your parabola? Second?
4 minus 1.
Which is?
Is
3. Okay. So 1, 3. Tickle my knee. Okay. Now, while we're there, let's just throw in a negative 1. When x is equal to negative 1, say again?
It's going to be negative 5.
Negative 5. Okay. Something wrong here.
Because you got 4 times.
Oh, yeah. Negative 1, yeah, is somewhere way down here. Okay, we'll find we're not going there because it has to be above the x-axis. So forget that. Bad idea. Well, how about 0? What would it be there? 0. So why is 0, 0 is going to be on there. Well, let's go over to 2. What would it be at 2?
It's going to be 8 minus 4. So it's going to be 4.
4. Okay. That'll be right there. How about 3?
3 is going to be 4 minus 9. 12 minus 9 is... So, I'm blanking out. 12 minus 9 is...
Pretty little black boxes when you need them.
I'm having brain freeze here.
3. Okay. Now, do you notice something here?
Yes.
That's a parabola. Anyone want to make a guess of the next value? Huh? 0. Let's see. When it's 4, 4 times 4 is 16, minus 4 times 4 is 16. Yes, that's 0. So here's your parabola part. We know we've got to be below the parabola and above the x-axis. Okay? So the only thing we don't know is this line, y is equal to negative 3x plus 6. You want to do that in a different color just for funsies? What color? Carolina blue. Okay? That's the light one. Okay? So let's pick some of those same values because we know we've got to be in there. When x is equal to 0, what is that equal to? The line. X equals 0. X equals 0.
It's gonna be 6.
Yeah, it's going to be 6. That's way outside the parabola. Not even interested in that. How about x equal 1?
This is gonna be way outside.
It-
No, not really. Because you got -3.
It's going to be what?
No, it's gonna be way out.
I can't. Okay. Well, yeah, on what value? Second? Okay, now x equal 3.
It's gonna be,
I mean,
it's gonna be
x equal 1. What is the y going to be equal to?
It's gonna be 3.
3. So yes, 1, 3 is right there. Right on that parabola. Next one. X equal 2.
It's gonna be 0.
0. Okay, so it's got to be above this. Well, this line's doing like this. So you're going to have to be above this, above that. Okay, that's the region we're interested in. See it? Okay. Now, it says find the area of that region there. We're going to call this R. Okay? I'm going to go back to black, not my Carolina blue anymore. Okay? Now, and by the way, this one doesn't go below the x-axis. Okay. Now, goodness, my eye hurts. Okay, if you're going to find the area here, notice this is not simply vertical or horizontal. Vertical, simple vertical here between those two lines, but here between those two lines. Horizontal between parabola and parabola, between parabola and line. Okay? I don't even want to start up here. I don't want to do parabola to parabola. So I think I'll do vertical, even though it's not simple vertical. Vertically simple. It is in 2 pieces. So break it into 2 pieces. Add this area with that area. And then you'll have the area, right? So let's do that. You want to use a different color to break it? Red? Okay. So this will be our break point right there. Okay. We'll cut off there and we'll do one little rectangle. I'll go back to our Carolina blue here. Do one little rectangle here. I mean, not one, but we'll do a representative one there. And then I'll go back to black maybe for the other one. And we'll do another little simple rectangle. Well, I didn't go to black, did I? Okay. There. Okay. So, let's do 2 integrals then. Let me go back to black this time. There we go. The first one will be going from, we're doing dx's, right? Both cases, do x's, right? Okay, what are the length of that rectangle from there? Going from the parabola to that line, right? Second?
So where are we going from?
The length of this rectangle is from the parabola up here down to the line right there, right? Yay or nay?
Yeah.
Okay. The width is dx. I'll get to that in a minute. So the parabola up there is 4x minus x squared minus a negative 3x plus 6. Right? That's the length, and our width is dx. Now, what are the limits on x that you're going from and to? X. No, x. 1. You're going from 1 to 2. Okay. There's the first part of that area. Okay. The second part of the area, okay, is going from the parabola to to 0. Y is equal to 0, right? That's this part, right? Okay. So that would be going from 4x minus x squared minus 0 dx, that's the thickness of it, and that's going from 2 to 4. 2 to 4. Perfect. Now, I realized right after I did this, I'm supposed to be doing this as iterated integrals. I forgot to do that. Okay. The outside is going to be just like we did here. The inside is going to be a dy here, and it's going from this to that down here. So I just skipped that step. Sorry, I forgot. And then this one's going from this to this, and then the inner one will be going from the parabola of this thing to 0 down here. I forgot that too. But then when you do that one, you get exactly what we've got here. Okay. Now, there's a little bit we can do to clean up that top one. This is the integral from 1 to 2 of 4x minus x squared, and then minus a minus is plus 3x, and minus a plus is minus 6 dx. Okay? And the next one's going to be fine. So we can combine like terms on this one. That's the integral from 1 to 2, sorry about that, from 1 to 2. 4x plus 3x is 7x minus x squared minus 6 dx. Okay? Let's do that integration. What would that be? Antiderivative of 7x squared. Help me. 7x, I don't know what it is. Huh? Second? I can't hear. Yeah, 7x over 2. 7x squared over 2, right? Antiderivative of x is x squared over 2. Okay? Minus x cubed over 3 minus, a little louder. Help me. I'm sorry? 6x. 6s. Okay, never mind. Okay, and that's evaluated from 1 to 2. Okay? It's just like crazy. I've got conjunctivitis in this eye, and it's stinging, pain in the neck or eye or somewhere. Okay, let's plug in the 2 first. 2 squared is 4. 2 will go in the 4. That denominator down there. That would be, yeah, 2. 2 times 7 is 14. Okay? Minus 2 cubed is 8 thirds. And minus 6 times 2 is 12. That's not looking too promising, is it? Okay? Minus, now let's do the same thing, but we're going to plug in 1 for the values there. 1 squared is 1, so that will be a 7 halves minus what's that? 1, the lower value. 1/3 minus 6, right? All right. Now, I don't know. My tendency is, let's just combine all of the integers together. 14 minus 12. Second? A little louder, I can't hear. That all comes up being minus 2/3, isn't it? Yes. Okay, minus 2/3. The top part is negative 2/3. And the bottom part, let's just go on and change all the signs. Minus, like that. Is that okay? All right. getting that in terms of 6, that would be 21 minus 21 6 plus 2 6. No, yeah, 2 6. And that would be minus 19 6. And that would be 36 6. Is what? 13 6? 17 6. That sounds better. Plus 17 6. And then combine that, that's minus 4 6. So that would be 13 6. Is that right? No. Oh, no. We aren't through yet. Okay. Huh? Okay. But that's just the first part. Now we've got to do this part. Okay. And I have more room here, so I'm going to do that. What's the antiderivative of 4x? Over, which is 2x squared, right? Yay? Okay. Minus antiderivative of x squared. X cubed over 3. This is evaluated from 2 to 4. Okay? So when we plug a 4 in there, 2 times 16 is? Yeah, 4 squared is 16. Right? Is that 32? Okay. Minus 4 cubed is 64 thirds, right? Okay. And then minus there, plug in a 2. 2 squared is 4. So that's going to be an 8, right? Minus 8 thirds. All right. Now, that top one, I mean the first one there, is, what's that, 96 thirds minus 64 thirds is 32 thirds, isn't it? Is that right? Huh? 64 thirds? Okay. So we'll say 64 thirds. Add that to 13 6. So that would be, yeah, that would be 128 6 plus 13 6 is what? What? Okay. 64 thirds plus 13 6. However you want to do it. I don't care. Okay, I can't hear.
47 2.
47 6?
47 over 2.
Oh, 47 over 2. Is that your final answer when you add those together?
Yes.
Okay. They got 15 over 2. We did something pretty seriously wrong there.
Maybe not. What do we have? It's 32 minus 64 thirds, right?
32 minus 64 thirds minus 8 plus 8 thirds. See, those are in parentheses.
Oh, okay. I
Okay. It's 32 minus 64 thirds minus 8 plus 8 thirds.
But that minus become plus, right?
What's that? Yeah. This is a minus, that's a plus. Yeah. Plus 8 thirds. 16 thirds?
Yes.
Okay, not 32 thirds, 16 thirds. Okay. So let's 16 thirds. And then add 13 6 to that. Yuck. Say what again? 15 over 2. That's what they got. Okay. 15 halves. Good. That's what they got. So that would be the area under that curve. When you need to split it into two either horizontally simple areas or vertically simple regions. And this did quite nicely in the two vertically simple regions. All right. That finishes 14.1. The homework exercises here. Any of the odds 3 through 9, they're all at Calc Chat. 3's at Calc View. Any of the odds 11 through 27, they're all at Calc Chat. 15's at Calc View. Any of either 29 or 31, they're both at Calc Chat. Either 33 or 35, they're both at Calc Chat. 33's at Calc View. Any of the odds 37 to 41, they're all at Calc Chat. 37's at Calc View. Any of the odds 43 to 49, they're all at Calc Chat. Any of the odds 51 to 59, they're all at Calc Chat. 53's at Calc View. 61 to 65, they're all at Calc Chat. 61, no, none of them are Calc View. You can explore doing 67 and or 69 if you want to think about them. Otherwise, you can let them go. They should both be at Calc Chat. You can do any of the odds 71 to 75. They should both all be at Calc Chat. Now, they say here you might need a graphing utility on this or a computer algebra system. You can try it without it, but you might find that pretty difficult. Okay? Then try number 77. Again, that might need computer algebra system. I don't know. Then there's a true-false number 79. That should be at Calc Chat. All right. Good deal. Oh, my eye hurts. So let's move on finally to 14.2. Staring at the screen doesn't do anything for my eyes. It makes them hurt even worse. All right. We'll go from current slide. And we're still in multiple integration. Now we're doing double integrals and volume. Well, we've been doing double integrals, but we've been calling iterated integrals. Now we're going to do what we call a double integral. Use a double integral to express, the other thing is all this glare off the floor. It sends my eye crazy because I guess it gets really light sensitive for this. Use a double integral to represent the volume of a solid region and use the properties of double integrals. We'll evaluate a double integral as an iterated integral, which we were just doing, and we will find the average value of a function over a region, which sounds like what we used to do with single integrals, too. It must be a two-dimensional function. So let's first look at double integrals and volume of a solid region. You know that a definite integral over an interval, a definite integral over an interval uses a limit process to assign measures to quantities such as the area, volume, length, arc length, mass, whatever. In this section, you use a similar process to define a double integral of a function of two variables over a region in the plane. Okay? So let's say we have a region here at the plane, and you've got x is going this way, y is going this way, and we'll do the integral over that region down there. Okay? Consider a continuous function f such that f of xy is always greater than 0. So if that's the xy plane there, the function f of xy is always up here in the positive part. Okay? The goal is to find the volume of a solid region lying between the surface given by z is equal to f of xy. So that's some sort of a surface up here, always greater than 0, above the xy plane. And the xy plane, so that's the bottom of it, is shown in this figure. Okay, now they just show something in the first octet where x is positive, y is positive, and z is positive. Okay? And this looks like some sort of a tent type area here. They have an R here, which I think is referring to the part in here. Okay? Not the part here. Okay? Because this is outside of that region. It looks like anyway. We'll have to get a little more better reading on it. Okay? You can begin by superimposing a rectangular grid over the region, as shown here. That's why they drew the outer rectangle here to set up the grid. Okay? The rectangles lying entirely within R form an inner partition, delta. Now, before we had deltas in a along the x-axis. Now we've got a two-dimensional delta, dx and dy. Okay, whose norm is the magnitude or the norm of delta is defined as the length of the longest diagonal of the end rectangles. Okay, so what if these weren't uniform? They look like these are uniform grids, so it wouldn't matter. But even if you had some that were longer, we'll use the norm as being the longest of those rectangles, whichever x or y. Okay? Now, next choose a point, x of 1, x of I, y sub I, that's somewhere in that, okay, in each rectangle, and form the, and you have I rectangle, well, you have some number of rectangles. I will go from 0 to whatever number of rectangles that is. To form a rectangular prism whose height is f sub I, f of x of I, comma y sub I. So this right here would be the height of that. Now it may be just touching or intersecting or somehow the surface here. Okay, that's going to be approximately the height of the ith prism. Okay, because the area of the ith rectangle, the delta a sub I, is your delta x times your delta y. There's your delta x, there's your delta y, so it's the product of those two. Okay? It follows that the volume of the ith prism would then be the base times the height. The base is delta x, delta y, and the height is the f of x of I, f of x of I, y sub I. Okay? You can approximate the volume of the solid by Riemann sums. That sounds interesting, of the volumes of all the end prisms. And that would be the summation from n, I equal 1 to n, or however many you have with n, of your f sub x sub I, y sub I, that's the height, times your delta A. And we're going to take all those delta A's to be approximately the same. Okay? As shown in this figure, and it looks like they're exactly the same. This approximation can be improved by tightening the mesh of the grid to form smaller and smaller rectangles, as shown in example 1. Oh, we haven't gotten there yet. Okay. We'll get there, and we won't enjoy it when we're there, I promise you. Okay. But anyway, the more rectangles you have, the better you are at approximating the volume. Okay, so here's example 1. Approximate the volume of the solid lying between the parabola, f of x, the paraboloid, okay, f of xy is equal to 1 minus 1 half x squared minus 1 half y squared, okay? And the square region R given by 0 less than x, 0, between x is between 0 and 1, and y is between 0 and 1. Use a partition made up of squares whose sides have length of 1/4. Okay, so you have 4 little squares inside that, so a total of 16 possible little squares. Okay, but you're not going to do the whole part. We'll do whatever part we need. Okay, so begin by forming the specified partition of R. Okay? Because this is going to be so hard to draw, I'm going to let them do the work for us. Okay? Let's go back to this. Here's our alphabet. Goodness gracious. Hurt. Okay. picture this now. Your x's are going to be 1/4, 1/2, 3/4, and 1. The y's are going to be 1/4. You might start with a 0. Okay, yeah. 0, 1/4, 1/2, 3/4, and 1. Okay? Now, when x is equal to 0, y is equal to 0, that's 1. So that's going to be that very first, right above the origin. When x is equal to 1/4, y is equal to 0, this would be a 1 minus 1/4 here. It hurts. I think it's that glare is just driving it crazy. See if it's better looking from this side. Okay. Okay. Say when x is 1/4, y is 0, this would be 1 minus 1/2 of 1/16. Okay, so you can figure all those and then do 0, 1/4 here and do that one. It's going to be a pain in the neck, but this is what it turns out. B. Okay. Oh, I see what they're going to do. These represent the grid points. Okay. Now, the very corner is 0, 0. We're not doing that. These are the interior. There's an exterior here, 0, 0 being here. Okay. And if you take the center of that thing, that's what they're doing. They're not doing one of the endpoints. This goes from 0 to 1/4, so that's going to be 1/8 here. 0 to 1/4 here, that would be 1/8. So the center point is 1/8, 1/8. This one would be 1/8, 3/8, 1/8, 5/8, 1/8, 7/8. Going this way, 3/8, 5, 1/8, 5/8, 1/8, 7/8, 1/8. Going this way, 3/8, 1/8, 3/8, 3/8, 3/8, 5/8. Yeah. Everything is going up in one dimension or the other by a quarter. So 1/8, 3/8, 5/8, 7/8. 1/8, 3/8, 1/8, 3/8, 5/8, 7/8. 3/8, 1/8, 3/8, 5/8, 7/8. So those are all the same. These then, when you get to the second row, the 3/8 here, 1/8, 3/8. So that gives you your entire grid. The last one out here would be 1/1. Okay? But you're in the center of that. All right. Now you start plugging these numbers in for your x and your y in that original function. And that's a pain in the neck. Okay? Because the area of each square is 1/16, 1/4 by 1/4, you're multiplying by the area 1/16. Now, your x, I, y, I, this really should have a comma in there. Oh, man. My knee hurts. What's that? I can't hear. Are we out of time? Oh, go back?
Can we do the problem next week?
Can we do the problem next week?
Yeah,
Or we?
the first example,
Okay.
You don't want to start it, you don't have enough time to finish.
Okay. Well, I was going to let you finish it at home. Wouldn't that be nice?
That's a pretty good idea.
Yes, you wanted to do that, didn't you?
Yeah.
I thought so. All right, thanks for suggesting it. All right. All right. But you see, the xi, yi, you pick that grid we just had up there and plug every one of those in.
All of them?
Well, yeah, as many as you feel comfortable doing. Okay, and you do that, and that's what you get as your answer. You sum all those. I went from 1 to 16. every one of those. And if you go back and check, I'm not sure that's right. You have a total of 16 here, so each one of these represents one thing. So, yeah, you plug each one in and add them up, okay? So that's what the n equal 1 to 16 was. Of all those x of I, y sub. This isn't quite right. I isn't going from 1 to 16. The points are going from 1 to 16. If you did this, this would be 16 by 16. That would be crazy. But it's really 1 to 4, I think it is, isn't it? Yeah, 1 to 4. That really should be a 4 right there. And that should be a 4. Okay. Then that would work, because you have, to give the idea, this is your f of 1/4, 1/4. This is f of 1/4, 1/2. You know, these are the value above that would be, no, that's not quite right. These are the XY values, and you have a total of 16 of those. But your I's are going from, that's what I was trying to say. This would be the 1, 1, 1, 2, 1, 3, and 1, 4. This would be 2, 1, 2, 2. You know, that, the thing. So you see your I's are going first I's and then J. Really, they should be doing I to J. They shouldn't be doing all I's, because the I's aren't the same. So it's just a sloppy notation is what I think it is. It is a total of 16 things, but they should each be, it's just a sloppy notation. I'm sorry. 1 to 4 on I, but then you're doing, it should be a double. J equal 1 to 4, and then this should be I, this should be J, okay, or something like that. That would be far cleaner, and that would get them all, okay. So they're a little sloppy on that. But when you do all that, for all 16 of those values, they say you get 0.672. I'll let you verify, okay?
So when we plug in the values, we're plugging them into I?
Okay. What you're plugging for your x of I, y sub I, you're plugging these in. You do this function here first for 1 minus 1/2, wrong way, 1/8 squared, 1/2 of 1/8 squared minus 1/2 of 1/8 squared. Next one you do, whichever order you do them, 1 minus 1/2 of 1/8 squared minus 3/8 squared from this one. And then you do all 16 of those. Their notation was sort of ugly, okay? But these are the 16 things you do. You plug each one of those in. Those are XY pairs. You plug them into the X and the Y, okay? Those 16. And this is what's supposed to get as an answer. Because you see, this is going to be a pretty small number. 1/16 of whatever that was, and then you just keep doing it. Okay? Some of those are getting incredibly small. In fact, some of them will probably be 0. Okay? So, possibly. Okay? Now, this approximation is shown graphically here. How much time do we have? Second? I'm sorry?
It's 2:02.
We're supposed to stop 5 minutes ago, 7 minutes ago. You didn't stop me, did you?
Well, that's what he was saying.
Oh, okay. So anyway, that's that approximation. If you then go to the exact volume of the solid is 2/3. Our estimate was 0.672. We overestimated slightly. So it should be 0.667. And we got 672. Not bad. Not bad at all. Okay? Now, I feel like I should show you why that's the volume, exact volume is that. Maybe we'll do that next time. But you see the blues here are where you underestimated, the purples are where you overestimated. So you see it came out pretty close. Pretty close. Okay. And that said you can obtain a better approximation using a finer partition. Now we're going to, with a partition of squares of sides 1/10, the approximation is 0.668, and it should be 0.667. Yes, quite a bit better, okay? So what would happen if you took the limit as the partitions are going to 0? That's going to be, we'll pick up there. Where are we then? I guess we're right about there. Okay. And that's where we begin next time. Good deal. Sorry we ran over a little bit.